Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today lecture we're going to continue with the title known as Faraday's Law. Okay, so we have discussed the introduction of Faraday's Law in our previous video. So with that, I'm going to continue today based on the information shown here, where we have been informed for Faraday's law, there are three conditions that we can apply, where the first condition is known as transformer EMF. For this particular case, we have been informed that the problem will involve stationary circuit, and the field, which is the magnetic field, will change with time. And then the second type of EMF that we can solve known as motional EMF, and the third category is known as hybrid EMF. So what I'm going to do in this lecture, I'm going to continue with the second and the third type of EMF. Okay, so with that, we're going to discuss about motional EMF. So for motional EMF, the conditions will be totally opposite to transformer EMF, whereby first condition, the B, which is the magnetic field density, constant. Okay, whenever we been informed where the magnetic field is constant, that is a good hint that the EMF need to be solved by using motional EMF method. And the second condition is involve moving parts. So I'm going to put here moving circuits. So whenever you see movement in your problem, where and also the B is constant with respect to time, that is known as motional EMF. So how actually we can solve motional EMF? So the VMF can be calculated using the standard formula that we saw before, where here you have to do the opposite to what we have done before. What I mean by that, before we need to differentiate first, but here what you need to do, you need to integrate first. So this is going to be your first task. You need to integrate. Okay, so that should be the first task. Once you done the integration, then only you going to do the differentiation. That should be the typical approach when you want to solve problem based on motional EMF. Yeah? So which is totally opposite to what we have seen for transformer EMF. But yet, let's say the problem given to you as such. So let's say you have this scenario in your problem. Yeah? So let's say in your problem you are given this type of condition. So you have a conductor. So let's draw it. So let's say this is a typical problem. Of what? Of a transformer, of motional EMF, where you have a conductor. So let's say this is your conductor. Okay, so and then you have usually this blue conductor is fixed, cannot move, and then you have another part of the conductor, the red one, which is movable. So what it can be shown here, so you need to have B. So let's say you have B. So B given by this black vector line. So this is our B. And we know that the B here is constant with respect to time. But yet we need to introduce movement now. So let's say we make this moving conductor to be shifted to the right. So let's say with velocity u. Okay, so I think it's much more practical if we use an equation which contain the information of u, rather than we try to solve this problem using the equation as is shown here, which does not contain the information of movement. Okay, so I think it's logical for us now to introduce another set of equation where we can solve for the motional EMF, and that equation containing the information of velocity. So now our task now to introduce alternative equation to solve or to solve motional EMF problem, but that equation will contain the information of u now, the velocity. So that's what our objective now, to introduce second equation that we can use. Okay, so let's say this is our first equation. So we're going to denote that as equation A. So now I'm going to introduce equation B, where contain the information of velocity u. So in order to do that, what we need to do here, we need to zoom into this particular part of the diagram. Okay, we zoom in. So what we're going to do now, I'm going to redraw this structure. Okay, this is part of the problem here. So this is our conductor. Okay, so now if I ask myself what should be the type of charge that we are dealing here, is it a volume charge, is it a line charge, or is it a surface charge? So I think because the structure is quite large, it's logical for us to assume this particular structure contain volume charge problem. Okay, therefore, since it's a volume charge, we're going to denote that as rho v, volume charge. Okay, so that should be the first thing. Then when we talk about volume charge, we need to take sample. Okay, so I'm going to take sample, because this is what we have done when we try to solve problem in the world of electrostatic. And the sample we're going to denote as what here? We're going to denote as dq. So, and then we can say now where dq going to be equal to what here? Good, rho v dv, based on volume charge model. So now we ask ourselves what happened to this sample. So since the conductor on the right here been shifted to the right with velocity u, so this sample also going to be shifted to the right with velocity u. Correct? So now the sample being shifted as what is going to follow the behavior of this conductor rod. And at the same time, as what we can see, the sample also been exposed to magnetic field B. Okay, so now we can see the sample going to experience two different type of vector. First, the movement vector. Second, the magnetic field vector. So then we ask to ourselves what happened to this sample dq due to the existence of the vector u and vector b. So in order to explain that, we have to go back to the idea of magnetic force. So I'm going to talk about magnetic force now. Okay, but for us to talk about magnetic force, is logical we discuss as well electric force, because they are similar. Okay, so I think magnetic force not been discussed before, but yet electric force we have discussed before, where we can easily state for electric force, D force equal to sample charge multiplied with electric field intensity. Correct? This is what we have seen before when we talk about Coulomb's law, when we want to introduce electric field intensity. So in terms of proper mathematics, I think we can rewrite this to be dF will be equal to dq, correct? This is what the charge that we are dealing here, dq, and then electric field is E. So we have been informed when you have a charge exposed to electric field intensity, force going to be created. Okay. So therefore, using that analogy, because I'm always mentioned to you, for magnetostatic scenario, always repeating electrostatic scenario. So I'm going to use that analogy now. I'm going to say to myself now, magnetic force dF, okay, going to be sample current, and then we're going to multiply with magnetic field density. Okay, so that should be the analogy now. This is what I'm trying to always to say to you all. Magnetostatic always repeating the concept of electrostatic. Okay, therefore I'm using that concept before to introduce magnetic force, where sample current, because we have sample charge before, and then we have field. So now we're dealing with magnetic field as what we have used electric field before. But what we have seen now, since sample current is a vector, magnetic field density also a vector. For this mathematic to be proper, I have to use cross product here. Because a vector cross another vector going to produce a solution of vector. Because force is a vector entity, therefore you must utilize cross product to make this mathematic correct. Okay, if you don't do this approach, so mathematically it's going to be wrong. So let's substitute now in terms of detailed mathematics now. So what type of current that we are dealing here? Is it a volume current? Is it a line current, or is it a surface current? Okay, because now we are said before, this sample is being assumed to be a volume charge. Now, this volume charge now moving. So what type of current that we can state here? Is it a line current, surface current, or volume current? Good, it's a volume current. So what should be the mathematic representing volume current? Vector J dV. Okay, that's a standard mathematical model we use to represent a sample of volume current. Okay, and then we're going to cross with B here. Okay, so that is slightly different than before. Before intensity, now density. Okay, so therefore this should be the mathematics. So if I substitute, okay, if I'm going to say to myself J equal to rho V U. Remember the model that we create before when we talk about current? So what type of current is this is known? Yes, convection current density. Okay, so that should be the one that we're going to substitute. Now what we're going to state now, dF, okay, I'm going to substitute now J with this term now. So what I'm going to have now, rho V dv u cross b. Okay, so what is our rho v dv? Yes, good. So now we are saying now should be dq u cross b. So what is it now? Let's go back to the diagram that we introduced earlier. So we are saying now, when a sample, this is the sample, correct? Been influenced by u, this is our u, as well as b, this is our b. What is going to be introduced in that mathematics? Yes, force. So now what happened to this sample charge dq as it been shifted to the right in the medium containing magnetic field upward? So this dq going to be forced in this direction. So this is your df. Okay, so that's what introduce the movement or creating a current in a circuit. That is the starting point, how current being created in a generator, and from the generator passing through the transmission line, and it's arrived at your house. Okay, so this is the source of current generation that you're seeing here. Okay, whenever a charge been shifted in a medium containing field, you're going to create the force. Force is the source of current generation. Okay, so therefore this is what you observe. Now, so mathematically, if I'm comparing this equation, so we call this magnetic force equation, with the electric force equation, what we can see, so if I'm comparing these two equations together, because they are force, I can see mathematically that E can be equal to what? Yes, U cross B. So actually when you have a movement in magnetic field density, you are creating electric field. Since this electric field is special, we call this electric field to be motional electric field. Okay, motional electric field. Motional electric field. Okay, so now let's recall when we talk about potential before. Okay, from the work of potential, okay, so from the work of potential, remember when we talk about potential in electrostatic field, we are saying E dot dl now no more equal to 0, equal to V EMF. Okay, remember when we talk in electrostatic, because the field there is conservative, this mathematics is equal to 0. But for this particular scenario, it's no more equal to 0, it's going to be equal to induced EMF. Okay, if I substitute E now with EM, okay, so now what I can say, in terms of mathematics, this VEMF can also be equated equal to U cross B dot dl. So this is alternative equation that we can use to determine motional EMF. So this is known as equation B. Okay, as a summary, when you want to solve for motional EMF, you can adopt two equations, either equation A or equation B, depending on the information given in the problem. Usually when the information containing the information of U, most probably the best method to be used is equation B. Okay, so that should be the objective here has been fulfilled, where we want to introduce alternative equation that we can adopt to solve motional type of EMF problem. Okay, so with that, inshallah, I'm going to continue with example. So let's do one more example here. Okay, the example, let's say you have a generator. So example now. Okay, so let's say you have a generator. So this is the blade of the generator. So let's say I'm going to draw this to be my y-axis. So this direction to be my x-axis. So vertical upward going to be our z-axis. So that should be our axis orientation. So let's say now you have the blade, where sometimes we call it stator in the generator, shown as such. So this is the blade. Since the problem is very simple, we're going to assume the number of turn here is only one turn. Practically, no, it's going to be more than one, maybe 1,000 or more than. The more the number of turn, the more current you will create it in the generator. So this is part of the blade. Okay, so let's say give dimension. So let's say the length of this particular structure, let's say make it to be L, whereby the width, let's make it to be H. Okay, so the black line is the conductor. So now, so to make this problem becoming motional EMF problem, what we need to introduce? We need to introduce there is magnetic field density B. But since this B is constant with respect to time, so I'm going to make it to be B naught. So this is your B. Okay, this is one part needed to create a scenario of motional EMF. Another information needed here is that this particular blade need to be moving. So let's say moving in these directions, omega radian per second. So the question, find VEMF. Okay, so that should be the question. So where is our VMF referred to? Here. So what should be the VEMF created by this particular conductor structure? Okay, so this typical structure that you can observe in a generator. Okay, so let's solve this problem. Okay, since this problem is known as motional EMF, correct? So we can adopt two approaches. The first, by utilizing equation A, and then another method that we can use here by using equation B. So for us now, since we are in the learning process, it's much practical if we are doing both methods. Why? Because you want to verify the outcome of both methods are agreeable to each other. Okay, so that should be our objective here, to prove to ourselves by using both methods we are having the same solution. So therefore, I'm going to use method B first. Okay, because I can see movement, so why not use that equation? So now this method, so now first method, I'm going to use method B. Once we solve this problem using method B, we're going to repeat this particular problem using method A. So just to verify our finding here. Okay, so now a solution now. So we are using method B now. So I'm going to using equation B. So what's this equation? State just now, VEMF equal to U cross B dot dl. Okay, so there you are. So this mathematics is very simple. Whenever there's a conductor moving in a medium containing magnetic field, you're going to generate EMF. That's what this equation can be concluded. Yeah? Whenever there's a conductor with certain length L moving in a medium containing magnetic field, we're going to create VMF. So that should be the summary of this equation. So now let's refer this equation, general equation, to our specific problem. So from this problem, what we can observe, the structure is a bit complicated. Why? It's not one line, it's more than one line here. So in order to make this mathematics systematic, the solution to be systematic, I'm going to split this particular structure into 4 different segments. What I'm saying by that, I'm going to say this part of this structure I'm going to label as site number 1. Okay, this particular part we're going to label as site number 2. So this we're going to label site number 3. And finally, this particular part of structure we're going to label site number 4. So then we're going to say to ourselves, when site 1 moving in the B, so you're going to have VMF, correct? So therefore, this site going to generate its own induced EMF. Similarly, this side also moving, okay, then it's also going to create its own induced EMF. So in systematic way, in simpler way, I'm going to say to myself, the structure can be redrawn to be such that site 1 going to create VEMF1 because conductor moving in B. And site 2 also going to have its own VEMF2. Okay, similarly, site number 3 also going to have its own VEMF3. And finally, site number 4 going to have VEMF4. So we can assume the structure now becoming batteries connected in series. So now our VEMF that been needed to be solved here can be summarized such that now our VEMF going to be equal VEMF of site number 1 plus V induced EMF of site number 2 plus V induced EMF of site number 3 and plus V induced EMF of site number 4. So that should be our systematic way to solve this problem. We're going to divide the complex structure to become simpler structure, and each simple structure going to produce its own EMF. And then we're going to sum all these EMF together to produce our final results. Okay, so now what I'm going to do now, I'm going to solve this EMF individually. So therefore, I'm going to solve for now VEMF1. So that's our objective now, to solve for VEMF number 1 or VEMF of site number 1. Okay, to do that, I'm going to redraw the problem to be in 2D. What I mean by that, I'm going to state now the axis coming out from this paper to be Y. So meaning that we are looking from this position. Now our eye is this position, so Y coming out. So the x-axis now should be in this particular configuration, and the z-axis is going to be as such here. Because why? We are looking from this position, looking to this direction. So Y coming out, X to the left, Z upward. So what I'm going to see now, I'm going to observe for this particular structure. From this position, what we're going to see, the structure now behaving as what? Yes, behaving as a dot. Correct? Because we're just going to see a dot from this position. So this dot is representing our side number 1. Okay, so what this dot actually doing? So this dot is moving. So I'm going to plot its loci. So this is what going to be observed. Okay, the movement of side number 1. You're going to create so this movement going to be rotating in these directions with omega radian per second. So that's what we observe now. Okay, so now we redraw this 3D problem into 2D problem, but yet we are only focusing on finding the induced EMF of side number 1. Therefore, what we're going to observe here as a dot, but the dot is creating this circular motion with a speed known as omega radian per second. Okay, so let's make it a bit clearer. So this is the plane of our blade. So now, okay, so now I'm going to use this mathematics. That's what we're going to do here. So to do that, I'm going to, as what we always do or did in EMT, we're going to take sample. So this is my sample now. Okay, my sample DQ. So now my sample is located here. DQ. Correct? So now what happened? So to find our EMF, so what we have to say in mathematically, because sample now D small v EMF number 1, remember this is only side number 1, will be equal to our equation B, which is U cross B, okay, and then we need to dot with DL. So that should be the step that we need to solve. So now how we define the U? The U here, is it angular velocity or is it linear velocity? Okay, let's go back to our original diagram. The U that we create before. So this U, is it linear velocity or is it angular velocity? Yes, it's a linear velocity. So therefore, we have to alter our velocity shown here, which is angular, okay, to become linear. So what I mean by that, since this sample is moving in this direction and this movement is known as angular velocity, to be converted into linear velocity, we must take the tangential of that angular velocity. So now, this is our U now. Okay, the U that you want to define in this equation must be represented in this format, because this is a linear velocity, even though the path number 1 is moving in angular movement, but yet this is what it does. We have to convert to linear velocity. So tangential wise mean that the angle between the U and the radius of the circle is 90 degrees. Okay, so that should be U in terms of diagram. But when we observe, because this position is not fixed, correct? This position can be located here. Okay, so if this DQ is located at this position, therefore the U going to be like this. Okay, if this position of sample DQ is located up here, the U going to be like this. So meaning the U in terms of direction is not fixed. It's changing based on where the sample DQ is being observed. So we have to now convert the U into a simpler approach. How we do it? Any idea how we able to convert the u in a simpler way so that we can substitute into these equations? Yes, we can observe from this simple structure, there are two directions remain fixed. What are they? Yes, the x-axis as well as the z-axis always remain fixed in this particular diagram. So it's much easier if we can split the u into that component. So what component? The u of x and the u of z. Because wherever the position of our dq, the u always contain the information of ux as well as uz. Okay, so now let's do that conversion. So how we do it? So this u going to be parallel to this vector. So what this vector is known, a unit vector an. Because remember, this structure contain area, and then this area has unit vector normal to the area, which is an. So this is 90 degrees, and luckily that we can observe the unit vector an to the surface surrounded by the loop is parallel to our u. So let's say this is the angle theta, and then we can say to ourselves the angle theta here also the same. So how we relate the angle theta with the information given in the problem? So what information given in the problem? The speed, which is the angular speed. So in terms of mathematics, we can relate the angular velocity with the theta. Okay, so I'm going to say now, in terms of mathematics, I can say that theta actually equal to omega t. Okay, how do I prove that? I'm looking at the unit of this symbol. What is the unit for angle theta? Radian, correct? What is the unit for angular velocity? Radian per second, correct? That's given by the question. And what is the unit for time? Second. So by looking at the unit, we can state this equation or this relationship is valid. So the theta, which is the angle between the z-axis and the unit vector normal to the area, is related to the angular speed by that particular movement of the blade. So therefore, I'm going to say to myself, what is ux? Ux going to be equal to, so I'm going to write now, the u actually can be represented as ux. What is ux? U magnitude and then sine theta. Okay, in which directions? Negative x directions, correct? And then I'm going to plus with second component, the uz, yes, u magnitude cos theta. Which direction? Negative z directions. Okay, and then how do I relate u and omega? U can be related to omega using the relationships known as omega multiplied with the radius. What is the radius of this particular movement? H over 2. Okay, so I'm going to take the magnitude to be omega h over 2. Okay, because the radius multiplied with the angular, you convert into the magnitude of the linear velocity. So now this equation can be rewrite. Okay, I'm going to do mathematics u cross b only. U cross b now. So I'm just doing that part of mathematics. Going to be omega h over 2 sine omega t negative x plus omega h over 2 cos omega t negative z. Okay, that should be the u, and then I'm going to cross with the b naught in z directions, correct? Okay, so let's do that mathematics now. We are doing u cross b only. Negative x crossed with the z will give us y. So what we're going to have now, y omega h b naught over 2 sine omega t. That should be the first cross product that we going to observe. Negative x cross z going to give us y omega b naught h over 2. That should be the amplitude and sine omega t. So let's do the second part of the mathematics. Negative z cross z will give us 0. So therefore the u cross b will end with this particular solutions. Okay, done. Okay, now let's go on to the second part of the mathematics, which is dl. Okay, let's observe dl here. So dl here is parallel to which axis that we can refer to. We have y-axis, x-axis, z-axis. So side number 1 is parallel to which axis? Yes. So now mathematically this should be dy y directions. Okay, because of the condition of side number 1 is parallel to the y-axis. So now what we're going to state now, that VEMF number 1 okay, going to be equal to integrations u cross b y omega h b naught over 2 sine omega t. Okay, that should be u cross b dot product with dy y. Okay, so now let's shoot the limit now. I'm going to integrate from where to where? From this point to this point. So what should be the limit here? 0 to L. So therefore what we're going to end this particular integration is going to be equal to y dot y becoming 1. So omega angular velocity h side L b naught over 2 sine omega t volt. Okay, that should be our VEMF side 1. So this is what this part of the term that we have solved here. Okay, so there you are. So that should be the steps that we can adopt in order to solve for this particular segment of the structure moving with angular velocity omega radian per second in the medium containing a magnetic field B naught Z direction. So the solution is as such. So we have to repeat with the other part as well, VMF number 2, number 3, number 4. So I'm going to repeat for now VMF number 2 now, just to show you the flow, how we able to solve this problem. So I'm going to focus now to solve for VEMF number 2. Okay, remember now what happened? We are focusing at this particular structure, number 2. So I'm going to repeat as what we have done for finding VMF number 1. I'm going to redraw this particular problem into two-dimensional. So let's do that. So y coming out, x to the left, and z upward. Okay, so if we look at our previous example, side number 1, when we observe from this position, it appears to be a dot. correct? Because you can see this side of the structure, you just see a dot here. But for side number 2, we're going to observe a line structure. Okay, so what happened now? Our line, or side number 2, going to be represented by this blue structure. Okay, this is our side number 2. Okay. Now, as I mentioned before, we have to take sample. The sample now can be anywhere on this particular blue line, which is our side number 2. So I'm going to take sample here. And then the sample distance from my y-axis, I'm going to give it to be r, because it's not fixed, because the sample can be shifted to any position. Therefore, the radius is also going to be changing. It's not fixed. So what happened to this sample dq? As what we observed before, you're going to have a circular motion. Okay, this is the movement of our sample dq with speed omega radian per second. And then remember what we did, we need to solve for dVEMF. Okay, let's rewrite that. I'm going to solve for dVEMF number 2. So that should be equal to U cross B dot dl. Okay, so now what is our U? Our U is the tangential directions as before. That is our U. And the U here is similar to the one we did before, which is equal to omega R, okay, sine omega t negative x directions plus omega r cos omega t negative z directions. It's similar as before. The only difference is the radius, because the sample now can be shifted along this blue line. Therefore, the radius going to be varies, not fixed. Whereby for side number 1, the radius is fixed. But in this particular scenario, the sample radius varies. So therefore, I leave it to be r. Okay, so now, using the previous example, if I do the mathematics U cross B, where U cross B now, what is going to be? Similar like before. Okay, because the B is B naught Z direction should be equal to Y. Omega R B naught sine omega t. That should be the solution of U cross B, correct? Okay. So now, how about the DL? The DL is here. So now, based on this diagram, what we can state now, the DL, okay, going to be represented with mathematics dx in x directions plus dz in z directions. So that should be our DL, because the sample, remember, should be located along this side number 2. So mathematically, it's going to be known as x component plus z component, because y is fixed, because this particular structure on the plane y constant, but the x and z varies. Therefore the DL must contain the x component, similarly the z component. Okay, so now let's do the mathematics now. So finally, what we can see, the VEMF of side number 2 is equal this term dot product with this term. So if I dot product y direction with the x direction, what is going to be the solution? Yes, 0. Similarly, if I do the y direction dot with the z direction, the solution also 0. So what we're going to observe now, the induced V EMF of the site number 2 is 0. So what we can say that V EMF of site number 2 is equal to 0. So that's why when you look for generator structure, the length always the site that produce the induced EMF. So therefore, when you look at the generator, always shape-wise to be long. Okay, because the width of this generator does not generate induced EMF. That's what we prove here. So therefore, when you look into practical generator, the length of the generator is very, very long. Yeah? Or the structure have a long structure, because what we can state here, we have been proven here, the width structure does not generate any induced EMF. So if you repeat this method yourself, okay, what you're going to prove that V EMF of site number 3 going to be equal to omega H B naught over 2 sine omega t, and V of EMF site number 4 going to be equal to 0. So our final solution, okay, so final solutions for total VEMF is going to be equal to, you have to sum all together, is going to be omega H, okay, I missed the L somewhere, yes, this should be L here, because you have to integrate from 0 to L, okay, L B naught sine omega t volts. So that should be the solutions using method number B. Method B to find motional EMF due to the rotation of conductor with the speed omega radian per second in a medium containing magnetic field B naught in Z directions. Okay, so I'm going to repeat the same problem now. I'm going to solve, not repeat the same problem here, using method number 2. Oh, sorry, method A. Hopefully what we're going to get from that, the coming approach is going to be the same as what we already done here. Okay, so I'm going to using equation A now. Okay, that's what we're going to do now. So what is equation A all about just now? VEMF equal to negative d over dt integrating B dot ds. Okay, so let's do it. So what we have to do, remember the first task that we have to do, we have to do the dot product first. So this is what you have to do, the dot product, the integrations. So this is going to be our first part. Then we're going to do the differentiation. So let's do that now. Yeah? So again, to make this problem solving simple, I'm going to create a diagram here. So I'm going to redraw the problem in 2D. So what I'm going to do now, y-axis coming out. Okay, x to the left, z upward. So I'm going to observe the area of the blade. So this is our area. Okay, so having width h, length L. So what does this particular structure doing? Is moving in these directions, omega radian per second. Okay. So what that we can see from this problem, first, the information of the B. So how are we going to draw the B here? Okay, the B going to be along the z-axis, correct? So this should be our B not z-axis. Okay, that's done. Now I'm going to determine about this ds. Okay, ds will be surface vector of the area, and that the area should be the area bounded by the loop. So how do I draw the vector? Good, the vector going to be drawn as such. So this is my vector ds. Okay, and then we know this angle theta. So we already defined just now, theta can be still equal to omega t. Okay, if I refer back to my dot product, so can we refer back to the dot product A dot B? Okay, so now if I do dot product B dot ds going to be B naught, and then ds, and then what? Cos theta. Remember the dot product A dot B is going to magnitude A multiplied with magnitude B and the cos angle between the two vector. So we have vector B and vector ds. If I do the dot product, should be B naught magnitude ds, the angle theta. So that's what I'm going to have based on the dot product. So now I have to integrate now with respect to s. So now what I'm going to have mathematically, so this is going to be equal to negative d over dt. I have to integrate now as B naught cos omega t ds. Okay, so what I'm going to have here, negative d over dt. So the solution now is becoming a B naught. So S is the area cos omega t. Is it correct? Mathematically, yes. So now let's find the final VMF. So now I have to differentiate step number 2 now. So VEMF is going to be equal to, now I have to differentiate respect to time. So cos will go negative sign, negative becoming positive. So what you're going to have? Omega S B naught sine omega t. Or we can sit now is equal to omega H L B naught sine omega t volts. So, and when you compare to our previous method, alhamdulillah, they are exactly the same. So that's proven our method here are correct. So that's how you always have to do in EMT or in your real world as engineer. You have to use various method, and then if the both method giving you the same solution, you can confidently state that your approach are correct. So this is what we are doing here. So we just use various method to solve for the problem of what? Of motional EMF. I'm going to do more example in my coming tutorial video, inshallah. So anyhow, you can do your own problem based on example extracted from our textbook. So what I'm going to do now is probably I'm going to repeat, I'm going to continue with our last type of EMF. Okay, so the third model of our EMF, I just named the model to be known as hybrid EMF. So in this particular cases, what we're going to see that the magnetic field density changing with time, similarly, you're going to have moving circuit. So that's going to be, and most of the problem that we're going to deal of Faraday law in real life going to be this time, because this is the most optimum design to generate induced EMF, because you are maximizing the parameter to generate induced EMF. So with this particular cases, what you have to do to find the EVMF is very simple. You can use the typical method we saw before, flux linkage over dt. So this is method number 1. Or you can use the VMF to be divided into transformer EMF, where you assume for this particular case that the B changing with time and the circuit remains stationary. Then you're going to add with the second condition you assume, motional EMF. Where in this particular case, you're going to assume the same problem, having constant B with respect to time, but the circuit is moving. Okay, so to make it related to equation we derived before, transformer is very simple. Negative the integration of dP over dt dot ds. Then if I'm using the first equation, dt integration b dot ds, or I can use this using the second equation plus the integration of u cross b dot d. Okay, so that should be the conclusion of my lecture regarding EMF. Okay, so we already relate EMF is related to Maxwell equation, and we already been informed that for electrostatic, the Maxwell equation is going to be equal to 0, but for electromagnetic, we're going to have the relationship between electric field with the magnetic field. So that's have been done. So we have seen 3 types of EMF, transformer, motional, and the combination of both. Okay, I'm going to solve more problem inshallah in my coming tutorial video regarding this scenario, these cases. So with that, thank you very much. Inshallah, we're going to see each other again. Take care. Assalamu alaikum wa rahmatullahi wa barakatuh.